Hello, everyone. Our names are
My name is Sai Herm.
My name is Brian Ho.
I'm Sean Kepke, and this is our project on recognizing malignant cancer cells using computer vision.
So first of all, acute lymphoblastic leukemia, also known as ALL, is a type of blood and bone marrow cancer, most commonly occurring in children. It is characterized by the development of too many lymphocytes, a type of white blood cell. Being an acute cancer, ALL progresses rapidly and can be fatal in a few weeks or months if left untreated. Symptoms of ALL can be mild and similar to that of other illnesses, such as fevers, easy bruising, bone pain, or enlarged lymph nodes. Typical diagnosis of ALL includes a physical, blood count, blood smears, and a biopsy. Because many of the symptoms are not specific to ALL, further testing is often required to make a correct diagnosis. Seeing a high amount of white blood cells and lymphoblasts in the blood may raise suspicions for ALL, but these numbers can vary from patient to patient, and a biopsy is often required to confirm diagnosis. Early on, the cells are underdeveloped, but produce in large amounts in the body. As a result, the body then stops producing lymphocytes, which puts the patient in a critical condition. A bone marrow biopsy is used to determine whether or not the patient has cancerous cells. The procedure is relatively quick at around 30 minutes of total operating time. However, waiting for the results can take 1 to 3 weeks, a potentially dangerous amount of time for patients. Our goal is to be able to leverage machine learning and image classification techniques to develop or at least show proof of concept of a quicker and more easily developable diagnostic system that could save patients valuable time while they wait for biopsy results. This project could potentially help with both the early detection and aftermath of a prognosis because determining the condition of a patient is vital in providing the correct treatment. For example, this project could be used to determine if there are any cancerous cells remaining after chemotherapy, and if there are, doctors can then proceed with the correct course of action.
So our project uses machine learning, which is an application of AI that allows computers to access data, recognize patterns, and implement deep learning techniques. Loading data into a machine learning program to test and train images will help the computer to learn using AI without explicitly programming the data. This algorithm will teach our program to recognize indistinct differences between healthy and cancerous blood cells. So using machine learning over traditional programming saves thousands of lines of codes by teaching the program to detect patterns and recognize data, instead of explicitly programming the model to detect and classify these patterns. As the image shown below, for traditional programming, you have a data and a set of rules that acts on the data and output an answer. For machine learning, on the other hand, instead of the programmer figuring out the rules, we give it answers with data and have the computer recognize patterns and figure out the rules, which is the basis for machine learning. So using machine learning, we are able to build a convolutional neural network that trains the program to detect cancerous blood cells. So CNN is a type of deep learning algorithm most commonly used for image classification. The idea behind CNN is that the images have to be filtered before they are trained in the deep neural network. After the images are filtered, features within the images become more distinct and the machine learns to recognize the pattern. So these image filters are basically a set of multipliers that manipulates the pixels of an image. As you can see in the image below, we can see that a set of multipliers, which is found in the red box, is multiplied to the pre-existing pixel values, which is found in the gray box. The multiplied values are added up to produce the next pixel value. So after an image is fed through the CNN, randomly initialized filters are passed through the image, which is then passed through the second layer, which is the dense layer, as you can see from the image. The filters that best matches the image output will be learned until the network is able to determine the correct features to distinguish between the different image classes. This process is called feature extraction. So we attempt to train our convolutional neural network to perform tasks such as image classification. So CNNs are able to detect patterns in the pixels of an image through the use of convolutional layers. These layers are then adjusted so that the input images matches their classifiers, which builds and defines the nodes of the neural network. The neural network must have a data set of labeled images for training and also another set of data for testing and validation. Training images using Keras and TensorFlow will allow users to create an image data generator that automatically creates labels for images based on the name of the parent directory. A training generator program is created to train data, and a validation generator tests and validates the images based on the deep learning results from training the model.
Our first attempt at creating a model consisted of adding various amounts of convolution and pooling layers in a sequential manner. The convolution layer applies a 3x3 filter with random weights to each pixel in the image, excluding the edges and corners. Each of these filters is considered a node in the neural network that is initialized with a random weight. As the model is trained and updated, the weights of the nodes are tweaked until the correct features in the images are able to be extracted. Pooling is essentially the process of compressing an image while extracting the edges and features that the convolution layer highlighted. For example, say we have a square image composed of 4 pixels in a 2x2 grid. Pooling would take the highest value of those 4 pixels, shrink from 4 to 1, and retain that maximum value for the remaining pixel. This process is applied to every 2x2 square of pixels, resulting in a new image that is 1/4 the size of the original. The pooling process allows for distinct features to be better highlighted, as well as reducing processing strain. While this model structure sounds good in theory, it was not effective for our data. The sharpening and compression from so many convolution and pooling layers led to the images looking too similar, and instead of highlighting key differences, it removed them. Because the differences between the image of a cancerous and healthy cell are so minute, shrinking the image down can often destroy the features that are needed to classify them. This model structure would have been more effective for classifying images that have much more distinct differences, like identifying different handwritten numbers.
So for making improvements to the model, we tried a variety of things. The first thing we attempted was to start from using prior weights from a previously trained model. Because time was an issue in terms of how long it took us to run each variation of the model, we decided to try training a new model starting from the existing weights of past versions, in hopes that it would only improve further and more quickly. The first time we started from prior weights, the model began with higher accuracy and a better loss value than before. It steadily improved and didn't fluctuate as much compared to the first run. However, when we loaded these weights onto a new model for the second time around, we found that the model began to overfit for the newest samples it was trained on, and performed worse when tested with other data. Continuing this process led to more drastic overfitting, where the more times we loaded prior weights, the worse the model performed on data not in the training set. We decided to switch to a different model structure to fix this problem. After doing a bit of research, we settled on the ResNet 50 structure. The residual neural network, or ResNet for short, was introduced in 2015 to solve a problem known as the vanishing gradient. It introduced the concept of skip connections, where the input of several convolutional layers is added to their output, creating a so-called skip connection. This idea ends up ensuring that the higher layers will perform at least as good as lower layers, and not worse. The ResNet structure is especially useful for very deep neural networks with up to 150 layers. We chose to use the ResNet 50 variant as we didn't have a need for that many layers. And while we didn't plan on utilizing the structure to its maximum potential, it offered us flexibility in adjusting our model to compare different variations. We also plotted the results to show the difference between model accuracy and validation accuracy, as well as model loss and validation loss, to get a better gauge of how our model was performing. We tried several different optimizer functions, being the SGD, stochastic gradient descent, ATOM, and RMS. The stochastic gradient descent SGD optimizer is essentially an approximation of gradient descent optimization, which is a first-order iterative process for finding the local minimum of a differentiable function. The SGD optimizer approximates the gradient by using a randomly selected subset of the training data, which speeds up the computation time with only slightly lower convergence rate. Because the SGD optimizer selects random subsets of data, it approaches optimizing the loss function in a random manner, but once it finds a groove, it will catch on to the pattern and optimize quickly from there on. Once it hits this point, the accuracy and loss steadily improve. The next optimization function we tried was ATOM. ATOM is an adaptive learning rate method, which means it computes individual learning rates for different methods. It gets its name from adaptive moment estimation, because it uses estimation of moments of gradient to adjust the learning rate for each weight of the neural network. It approaches optimizing the loss function very slowly, but it has guaranteed improvement throughout each simultaneous epoch. Unlike SGD, there are little to no random spikes in accuracy and loss with Atom. The performance will converge steadily and slowly, meaning it requires more epochs to achieve better performance, but it will consistently reach that level of performance. The third optimization function we tried was RMS prop, or root mean square propagation. This optimizer uses the magnitude of recent gradients to normalize the total gradients. Essentially, it divides the current gradient by the root mean squared gradients, leading to a very robust optimizer. Our results showed some similar performance to the SGD optimized model with even larger oscillations. The end result varied wildly based on how the optimizer performed for that specific epoch, but using the best checkpointed version throughout the total run yielded excellent results. Another thing we varied was different training sample sizes. Changing the amount of labeled samples does in fact impact the accuracy and loss of the model. As assumed, more samples make for a better model. The trade-off for us came down to compute time. Having a smaller training dataset allowed us to run more epochs in the same amount of total time, whereas training a larger dataset led to better approximations with more stable improvements with each additional epoch. The ideal scenario would be to train on as much data as possible and as many epochs as possible, but time was a critical factor for us due to our limited hardware. In order to test a wide variety of models in time, we needed to limit our sample sizes. Using too small of a dataset led to overfitting the training data, with poor predictions on everything else, while using too large of a dataset was simply not feasible for testing different variations in time. For the SGD optimizer, using a smaller dataset led to large oscillations in accuracy and validation loss. However, the best model checkpoint gave almost identical performance compared to the larger dataset run. For the Atom optimizer, both variations showed slow and steady improvements with each additional epoch, with the smaller dataset variation having about 10% worse accuracy and validation loss. Our first test used the SGD optimizer with 500 training images, 204 validation images, and 512 nodes in the network. While the model loss and validation resulted in good curves, the validation loss and accuracy fluctuated rapidly until converging at suboptimal values. As you can see, the validation loss gradually increased at the end, and the validation accuracy decreased. The bright side is that the best model checkpoint from this run performed decently, despite the end result being poor. After increasing the number of nodes in this network, we found a mostly more stable curve for both the validation accuracy and loss that seemed to converge. Despite the drastic spikes at the end, the best performing checkpoint from this variation is noticeably better than the previous iteration.
Building on top of what we learned from the other iterations, we decided to add more training data to the set and keep a large amount of nodes. We can then see that the loss and accuracy has a much better convergence, with the validation loss hovering around 0.8 and accuracy around 86%.
Our first run with the Atom optimizer yielded a steadily improving model that came up a bit short. Each subsequent epoch yielded better accuracy and loss, but the increase in performance was very minuscule. This gradually changing variation needed more epochs to reach a satisfactory performance.
Using a larger training set, once again, showed better results, although it's very slight. Our validation loss is much more in line with the loss produced from training. Also, our validation accuracy is much better than the prior run with an accuracy of 84%. This optimizer seems to benefit the most from a larger training data set. Just like before, this variation needs more epochs to reach its optimal performance. Similar to SGD, this optimizer produced drastic oscillations in both the validation accuracy and the validation loss. Unlike SGD, however, the curve never converged at a steady value. While this appears to be a bad model, if we consider the best checkpoint throughout the oscillations, we come up with the best performing model yet. At about 0.5 validation loss and 92% validation accuracy, this checkpoint has outperformed all our other models we have tested thus far.
So there are a couple of problems we encountered when building our model. First of all, we had very limited hardware in terms of how much RAM and GPU memory, which led to very slow runtimes. Single model runs could take up to a week. We also looked into cloud computing, but deemed it too complex and expensive to be able to test as many variations as we had liked. Additionally, the lack of processing power limited our ability to make quick changes. If a model had an error or some images were mislabeled, we had to wait the entire runtime to be able to fix it. This led to slow progress and made it take much longer to learn from failed models. Lastly, our initial model structure was informative, but ultimately useless because of how it destroyed the key features of our images. We ran quite a number of variations with it looking for improvement, but none made significant differences, and we switched to a new architecture entirely. For our future work, there are a couple of things that we could improve on. First of all, we need to attempt a longer run with significantly more epochs. This may give us the results we have been hoping for. Furthermore, we want to also run a test with a much larger data set, around 2,000 images. We would also like to rerun some prior iterations with tweaked hyperparameters to see if the model structure was good, but lacking the correct optimizer parameters.
Moving on to the demo portion of our code. Here we have our import list for importing all the necessary libraries and functions. We define the directory locations for our healthy and cancerous cells. We begin the starting time of the code to determine how long it took. And in here, we define the desired dimensions of our images because the actual input is 450 by 450, but that's a little too large and not ideal for our model. As you can see, we print out the number of training samples and validation samples to make sure that we are using the correct folder. And in here, we define some of the key parameters for our model. The number of classes, which is 2 because it's just binary, it's just cancerous or healthy. The number of epochs, which is the amount of times the entire data set will be run through the neural network. The batch size, which is the number of images run through the neural network at one given time, and then the current trial number we're on. So this is my 12th trial number. Then we define the ResNet 50 structure, and this is just some of the default parameters used. And we also define the output layers of our model. As you can see, the 4096 nodes here. This checkpoint section of the code will save the best version according to the validation loss thus far, and will only update if the model sees a better validation loss after a new epoch has run. Here we define some of our optimizers with the hyperparameters, and we chose which one we wanted to use right here. So this run in particular was for the Atom optimizer. And this function, model fit generator, basically runs the entire section of code and trains our network and tests it with the validation data. And these two just simply plot our data from the graphs you saw in our presentation.
So moving on to the output, first of all, we, as Sean said before, we look at our training images, make sure we had enough, and make sure we had the right file path. We printed an example of the image, just so we know it's like the correct image that we're using, right up there. After that, we print the model parameters. That way we know which kind of model we're using, how much memory it takes up, how many parameters it's going to use. So we understand how much processing power it's going to require for our computation. After that, we go over our epochs. So each epoch, we list out how many steps, how long it takes to do all the steps. And then we list out both the training loss and the training accuracy, as well as the validation loss and the validation accuracy. Afterwards, we print every epoch, so we can see the validation loss and the validation accuracy increase or decrease, as well as usually the training loss and the training accuracy goes up and down consistently. For Atom specifically, we can see a consistent improvement for the validation loss and the validation accuracy. And that's how our model was anticipated to work, at least this specific model. Afterwards, we print the final accuracy and final loss, as well as export the image files so we can actually look at the graphs for the presentation. And lastly, we have the program runtime, so we know how long computation took. This is so we can approximate and change parameters for how much files we use to train. So if we wanted lower computation time, we'd change some parameters such as the nodes or how many images we put in. That way we can have a faster computation and see like anticipated results or approximate results.
In this section of code, we go through how we test the model after we've saved it. basically we just load in a model, we iterate over all the files in a specific directory. In this case, it's our testing set for only healthy images. And after it gets all of those in an array, it basically goes through and identifies if the prediction weight is less than 0.5. And if it's less than 0.5, it tallies that it's incorrect, because all of the second column should be healthy cells, which should be greater than 0.5. This is printing out basically the predictions for every single image that we loaded in, with each of these being a weight for its prediction of it being that particular type, cancerous and healthy. As you can see, for the majority of these, it got it right. It got greater than 0.5 for the healthy section. And in the end, we print out the accuracy across the whole thing, which was about 82% in this case.
So this has been our project on recognizing malignant cancer cells using computer vision. Before we sign off, we'd like to give a huge thank you to Dr. Kang for helping us advise us on our senior project. We also like to thank you for taking the time to watch our video. Once again, thank you very much. Have a nice day.